Hello everyone, welcome to MG Academy. The next topic in data structure is AVL tree. So AVL tree is a type of binary tree. Type of binary tree. That is, the nodes of this tree will have at the most two children, either 0, 1 or 2. Okay, any one like 0 children, 1 or 2, but not other than this, because it's a binary tree. Then second, it follows the property of binary search tree. Binary search tree. Okay. Now what is a binary search tree? See, suppose this is the root. Then this is left subtree. And this right subtree. Okay. So in a binary search tree, the nodes in the left subtree have values less than the root node. Means left subtree. So the nodes of left subtree have values less than root. And this is right subtree. So nodes in the right subtree have values greater than root. Suppose if the value of the root node is 100. So now the nodes in the left subtree will have values less than 100. And nodes in the right subtree will have values greater than 100. Okay. So this is the logic of binary search tree. So if you don't know what is binary search tree, then please check the link in the description box below. I have already created a video on that. Okay. So check it out. Then AVL tree is a self-balancing binary search tree. It is a self-balancing binary search tree. So now how we are going to see whether the particular tree is a balanced or not? By calculating the balance factor of each node in the tree. So calculate balance factor for each node in the tree. So we have to calculate what? Balance factor. Now how this balance factor is calculated? See, height of left subtree minus height of right subtree. Okay. So with the help of this formula, we are calculating balance factor, and the value of this balance factor should be either 0, 1 or minus 1. The value of balance factor should be 0, 1 or minus 1 for each node in the tree. And if the value of balance factor is other than this, then that tree is not an AVL tree. So there are two things. The first thing for a tree to be AVL is that it should follow the property of binary search tree. And the second thing is that the balancing factor should be either 0, 1 or minus 1 for each node in the tree. Consider this example. See. Okay, this is the root 12. So now this is an tree. So first we'll check whether it is a binary search tree. So see, the nodes in the left subtree have values less than 12. 9, 11, 7, 10. These values are less than 12, right? The nodes in the right subtree have values greater than 12. 18, 15 are greater than 12. Yes. So this tree is a binary search tree. Means this tree follows the property of binary search tree. Now what we'll do? We'll calculate balance factor for each node. See, here 10. The height of left subtree for node 10 is 0, right? And the height of right subtree for node 10 is 0. So 0 minus 0 is 0. Isn't it? So the balance factor for this node is 0. Now 7. So right and left subtrees of this tree of this node 7 have height 0. So 0 minus 0, 0. Now 11. So here left subtree height is 1 and right subtree height is 0. So 1 minus 0 is 1. Right? 1 minus 0 is 1. Then 9. Left subtree height is 1. Right subtree height is 2. So 1 minus 2 is minus 1. So what is the balance factor for node 9? Minus 1. Then see, root node 12. Left subtree height is 2. No, 3. 1, 2 and 3. See, so left subtree height is 3 and right subtree height is 2. So 3 minus 2 is 1. Okay. Then 18. Left subtree height is 1, right subtree 0. So 1 minus 0, 1. And 15. Left and right subtree height is 0. So 0 minus 0, 0. Okay. So you can see that this tree follows the property of binary search tree, and the balancing factor for each node in this tree are either 0, 1 or minus 1. So this tree follows both the conditions. So this tree is an AVL tree. Okay, see, and one more thing about AVL tree. So AVL tree is a balanced tree and this balancing is based on the height, isn't it? So the AVL tree is also called as height balanced tree. Height balanced tree. Okay. Now suppose if we want to insert another node in this tree. See, I'll insert one more node in this tree. Now, after inserting new node in this tree, again we have to check the balancing factor for each node. So the balancing factor for node 10 is 0 because left and right subtree height is 0. For 13 also it is 0. For 7 also it is 0. For 11 it is 1 minus 0. So 1. For 9 it is 1 minus 2. So minus 1. For 12 height of left subtree is 1, 2 and 3. And height of right subtree is also 1, 2 and 3. So 3 minus 3 is 0. Then 15. Left subtree height is 1, right subtree 0. So 1 minus 0 is 1. 18. Left subtree height is 1, 2 and right subtree height is 0. So 2 minus 0 is 2. Balance factor for node 18 is 2. So according to our condition, the balance factor should be either 0, 1 or minus 1, and here the balance factor for this node is 2. And because of this tree is not an AVL tree. Not an AVL tree. If the balance factor is other than this 3, then that implies that particular tree is not an AVL tree. So for restoring our destroyed balance condition, what we'll do? We'll do rotations. Now let us study rotations in AVL tree. Okay, so what are rotations in AVL tree? Some modification done on AVL tree in order to rebalance it is called rotations in AVL tree. See, if the balance factor of a node in AVL tree becomes other than 0, 1 and minus 1, then that tree is not balanced, right? So for rebalancing it, we have to do some modifications. So modifications done on AVL tree in order to rebalance it is called rotations in AVL tree. That modifications are nothing but rotations of AVL tree. Okay. So there are 4 types of rotations in AVL tree, and those are LL, RR, LR and RL. Out of this, LL and RR are single rotation. Single rotations. Okay. And LR and RL are double rotations. Why so? These two are single and these two are double. You will get the reason when you will see this 4 types of rotations. You will get the reason why these two are single and why these two are double. Okay. So the first one is LL rotation. LL rotation. Now consider this tree. Suppose this is the tree given to you. Now first thing what you will do, you will check the balance factor for each node. So balance factor for node 10 is 0 because 0 minus 0 is 0. Balance factor for 20 is 1 minus 0, that is 1. And for 30 it is 2 minus 0. So 2. So you can see that the node 30 has balance factor 2, which is not acceptable, isn't it? Because the balance factor should be either 0, 1 or minus 1. And if the balance factor is other than this 3, then that tree is not balanced. So this is not balanced. Now why it is not balanced? Because 20 is attached as a left branch to 30. 10 is also attached as a left branch to 30. And because of these two left branches, this tree is imbalanced. So this is LL type of imbalance. So for that reason, what we'll do? We'll perform LL rotation. And in LL rotation, what we do? We rotate the tree in right. So we'll rotate this tree in right direction. And after rotation, what we'll get? We'll get 20 as the root. 30 will be pulled to the right of 20 and 10 will be to the left of 20. See, like this. 20 will become the root. 30 will be pulled. It will be attached as a right subtree to 20 and 10 will be left subtree for 20. Okay. Now again we'll check the balance factors. So the balance factor for this node is 0. This 0. 20 is 1 minus 1, that is 0. Okay. Now the balance factors are maintained. The binary search tree property is also maintained. See, left subtree node have value less than 2 and right subtree node have value greater than 1. So binary search tree property is also maintained. Now this tree is balanced. So this is LL rotation. The second one is RR rotation. RR rotation. Okay. Suppose this is the tree given to you. Now because this 20 and 30 are attached as right subtrees to 10, the value is greater than the root. 20 and 30 is greater than the root, that is 10, isn't it? Because it is binary search tree also. Because AVL tree follows the property of binary search tree also. So 20 and 30, because they are greater than 10, they are attached as right subtrees of 10. Okay. Now first thing what we'll do, we'll check the balance factors. So balance factor of this node is 0. 20, 0 minus 1 is minus 1. 10, 0 minus 2 is minus 2. So again, the balance factor for this node became minus 2, which is not acceptable. Now why this is not balanced? Because of these two nodes, because 20 is attached as right branch of 10. 30 is also attached as right branch of 10. So because of these two branches, right branches, this tree is imbalanced. Hence this is RR type of imbalance. So we'll perform RR rotation on this tree. So in RR rotation, what we do? We rotate the tree in left like this. Okay. And after rotation, what we'll get? We'll get 20 as the root. 10 will be pulled. It will be to the left of 20. Like it will be left subtree for 20 and 30 will be the right subtree for 20. Okay. Like this. 20 will be the root. 10 will be to the left of 20 and 30 will be to the right of 20. Okay. Now the balance factors are maintained. Binary search tree property is also maintained. Correctly, see, 10 is less than 20, 30 is greater than 20. So binary search tree property is also maintained. Balance factors are also maintained. So now this tree is balanced. Okay. So this was RR rotation, right? Now the third type of rotation is LR rotation. Okay. Suppose this is the tree given to you. Like this. Okay. Now first thing what we'll do, we'll check the balance factors for each node. Balance factor for this is 0 because 0 minus 0 is 0. For 10 it is 0 minus 1. And for this 2 minus 0. So 2. Okay. Now the balance factor for this node is 2, which is not acceptable. So this tree is not balanced, right? Now why it is not balanced? Because 10 is attached as a left subtree for 30 and 20 is attached as a right subtree for 10. Okay, so this is LR type of imbalance. For that reason, we'll perform LR rotation. Okay, LR rotation will perform. So this is a two-step process. Two-step process. Okay, and therefore it comes under the category of double rotation. In first step, what we'll do, we'll convert this LR type of imbalance into LL type of imbalance. So for that reason, like this, LL cap means like this. We have to convert this structure into this. Okay. So for that reason, what we'll do, we'll ignore this root node. Means we'll keep this root node as it is. And here, with these two nodes, we'll perform left rotation. Like we'll rotate these two nodes in left direction. Like this. In left direction. So when we'll rotate this node, these two nodes in the left direction, what will happen? 20 will come in place of 10 and 10 will be pulled down like this. Now 20 will be here and 10 will be pulled down. Okay. So now we'll again check the balance factors. So balance factors are 0. 20 is 1 minus 0, that is 1, and 30 is 2 minus 0, that is 2. So again the balance factor of node 30 is 2, which is not acceptable. And what is this? This is LL type of imbalance. So now we'll perform LL rotation. We have already seen that. So in LL rotation, what we do? We rotate this tree in the right direction. Like this. So if we rotate this tree in right direction, what will happen? 20 will become the root. 30 will be pulled down. It will now become right subtree of 20 and 10 will be the left subtree of 20. Okay. Now again we'll check the balance factors. So the balance factors are 0, 0, 1 minus 1, 0. Right. So now the balance factors are maintained for each node. Okay. And binary search tree property is also maintained. So now this is balanced. So we did two steps. In first step, what we did? Rotate towards left. Right? We ignored this root node and we made these two nodes to rotate in left. To rotate towards left. In second step, what we did? Rotate towards right. Okay. So step 2. Right. So this is a two-step process. Hence it is double rotation. Now the fourth is RL rotation. Okay. Suppose this is the binary tree given to you. Okay. Now first thing what we'll do, we'll check the balance factors. So balance factor for 20 is 0 because 0 minus 0 is 0. For 30, the balance factor will be 1 minus 0, that is 1. And for 10, the balance factor will be 0 minus 2, that is minus 2. Okay, so for root 10, the balance factor is minus 2, which is not acceptable. Hence, this tree is not balanced. Why it is not balanced? Because 30 is attached as the right branch for 10 and 20 is attached as the left branch for 30. So this is RL type of imbalance. So now we'll perform RL rotation. Okay. So RL rotation is also a two-step process. Two-step process. Okay. In first step, what we'll do? We'll convert this RL type of imbalance into RR type of imbalance like this. So now we want this type of structure. So now what we'll do? So now you'll say that I'll just attach 20 here and then I'll get this structure. So you can't do that because AVL tree is also a binary search tree. So if you attach 20 here, then it will not maintain the condition of binary search tree. Okay, so for that reason, the first step will be rotate towards right. Rotate towards right. We'll ignore this root. We'll keep it as it is. And now we'll rotate this towards right. Then when we'll rotate these two nodes towards right, what will happen? 30 will come down and 20 will take its place. So now 20 will be in middle, 30 will be down. Okay, like this. Now again we'll check the balance factors. So the balance factors will be 0. 0 minus 1 is minus 1 and 0 minus 2 is minus 2. So again this tree is not balanced. This is RR type of imbalance. We have already seen RR type of imbalance. So in that case what we do? We rotate the tree towards left. Like this. Rotate towards left. And after that what we'll get? Rotate towards left. What we'll get? We'll get 20 as the root. Right? 10 will be pulled down. It will become left subtree of 20 and 30 will be to the right of 20. Okay. Now again we'll check the balance factors. 0, 0, 0. So the balance factors are maintained and now this tree is balanced. So it is also two-step process. Step 1, step 2. Okay. So this was RL rotation. And because LR and RL rotation requires two steps to become balanced, it comes under double rotation. LL and RR requires only one step to become maintained. So it is single rotation. Okay. So that's it for today. Hope you understood my today's lecture. And if so, then give this video a big thumbs up, subscribe to my channel and share it with your friends.